Welcome to the S4GEO Podcast. I'm Rodger Baker. This series is designed as a dialogue between geopolitical risk professionals and a variety of industry and technology specialists, corporate officers and government officials, scientists, academics, and other practitioners to gain insights into the myriad ways in which geopolitical dynamics are impacted or impact the global business environment. Today, I'm pleased to be joined by Marcus Gomez and Michael Hochberg, both with extensive experience in the semiconductor and high technology sectors. Marcus is a multi-time founder who formerly built Luminous Computing. He's currently advising large venture capital funds. Michael has been a physicist, entrepreneur, professor, and corporate executive. He has co-founded 5 successful semiconductor companies and now spends his time on issues of policy, geopolitics, and strategy. Thank you both for joining me.
Pleasure.
So we know that technology is a key part of understanding geopolitics. And that's whether it shapes our relationship to place, such as through shipbuilding, aircraft, canals, how it affects societies and labor. We can think of the printing press, the telephone, the internet, how it impacts military and the military space, such as, the invention of the tank, the aircraft carrier, hypersonic missiles. Today, for our discussion, we're going to take a very small nibble at a very large topic, and that is semiconductors and artificial intelligence. We're going to look at it from both the perspectives of technology and the perspectives of geopolitics. And we need both of these. The geopolitical significance is often misleading if we don't have a strong understanding of the technology, and the technological features that will be adopted, rejected, or adapted in different ways often reflect underlying geopolitical patterns. So to kick things off, I'd like to begin with sort of a few definitions to put us all on the same page to set the stage for what we're talking about. On the physical technology side, I think let's start by defining what are the various steps and stages of a semiconductor supply chain. And then more on the computing side, what do we really mean from a technological perspective when we're talking about artificial intelligence, as opposed to sort of the popular perspective of how people understand that?
So the way that people talk about this publicly is they talk a lot about chips, right? But chips are only one very small part of this ecosystem. They're a critical part, but they're one small piece. When you think about this, at one end of this supply chain, you have raw materials, sand, which is where you get your silicon. You have indium, you have phosphorus, you have helium, you have all of the different raw materials that come in one end of the supply chain. And then at the other end of the supply chain, you have data centers that are filled with racks of computers that people are logging into to use for AI applications. In between, you've got several major stages, right? The first is that you have the companies that turn those raw materials into the raw inputs for making chips. So chips don't start as chips. They start as, for instance, if you're talking about silicon chips, they start as giant single crystals of silicon that are a couple meters long, maybe half a meter wide, and that are grown in a giant melt zone furnace, right? Those things are then sliced up, polished, and turned into the wafers that go into what's called a front-end semiconductor fab or a foundry. Now, that foundry has many inputs. It's got fine chemicals. It's got machines that are vacuum systems and lithography systems that actually pattern those wafers, etch those wafers, deposit materials onto those wafers. You've got resists that are primarily made in Japan that allow you to actually do what's called photolithography on those wafers. And then you have equipment that's used for testing those wafers. So you've got equipment, you've got software, you've got raw materials. All of those things come together to get you a wafer that has patterns on it, where those patterns are billions and billions of transistors in a single chip. And in fact, there's IP ecosystem as well, where you have inputs of intellectual property, where you pull together many different companies' designs in order to build the chip. But from the chip, then the next level is you have companies that take multiples of those chips and assemble them together into a multi-chip module or a package. You have those packaged chips where you have a chip that's inside of an organic or a metal box. Those packages get put onto a board. Those boards get put together into a computing system, and those computing systems get assembled into a rack that gets delivered into a data center. At each step of that process, you have additional materials, you have multiple different kinds of chip fabs that are all producing different chips that get put together. There's memory, there's CPUs, there's optical chips. And at each stage, you have equipment and you have design and you have IP and you have all of these different pieces that have to come together.
And we'll come back to this in a moment, but within that also you end up with various geographies where certain pieces of this are stronger, certain pieces of this are weaker. And this is what we'll get into in a minute here on the complexity of these supply chains.
Absolutely. There's a very strong incentive toward clustering in this field because every step of this process requires very specialized knowledge and specialized experience, where a lot of it is stuff that's hard to write down. And so if you're building a fab, the cheapest place to build a fab is next to one where you can poach people who already know how to do stuff so you don't have to train them from scratch.
And let me jump to you, Marcus, really quick here on the AI side of things. When we talk about artificial intelligence, of course, there's the popular views of what artificial intelligence is. There's a lot of notes that come screaming around telling people, well, there's 10 different kinds of artificial intelligence. You have to know what they are. What do we really mean when we're talking about artificial intelligence, and how should we think about that also in relationship to this semiconductor supply chain?
Yeah, so when we talk about artificial intelligence now, I think it's interesting because if you roll back the tape 5 years, people had wildly different ideas of what artificial intelligence would be. Because there weren't really that many deployed applications of this stuff. To first order, I think everyone's model of what artificial intelligence is today is correct because, OpenAI has nearly 1 billion active users. The thing that you talk to when you talk to ChatGPT is actually a pretty accurate representation of what we mean when we say artificial intelligence. What's running in the background there is a large model that has been trained across the entire corpus of all human text, so everything humans have ever written, sometimes comically collected in comical ways and absurd ways, and they run on large clusters of the computers that Michael described. So one model today that's a state-of-the-art model might run on a box of 32 or 64 or 128 GPUs, and it might be serving dozens or hundreds of users in parallel.
Well, I mean, I think the issue that people run into with artificial intelligence is sort of the raging debate as to whether AI is intelligent or not. How does it work? What is it really doing behind the scenes? And this is going to come to the question of how do we think about artificial intelligence in its relationship to labor and tasks? Yeah. In other words, what does it do? What doesn't it do? What does it do well? What doesn't it do well? And how are those going to evolve, and how may that impact work?
Every model goes through. I'll describe a little bit about how the models are trained, and that'll actually give a really clear picture for how to figure out whether or not your job is going to disappear in 6 months. So the models basically go through two big phases of training. There are lots of intermediate steps, but the two big ones are pre-training, where they're, like I mentioned, they're trained over the entire corpus of human knowledge, and everything that's ever been written down everywhere in books, on the internet, under Michael's mattress, whatever's hidden there. And then there's post-training. And post-training is where the model, the easiest way to think about it is the model will be deployed live in some context, and will get positive or negative feedback signals. So, for example, when you're using ChatGPT, sometimes you'll see a note that says, "Hey, was this response helpful?" Or sometimes you'll see two responses that it'll ask you to choose. That's called post-training, where it's now it's one phase of post-training where the model is being given some live feedback beyond just trying to predict the next word across the corpus of human text. And that post-training phase is used to do a lot of things. It's used to align the model's values. It's used to make the model very good for particular contexts, and those contexts might be coding, it might be working on a spreadsheet, it might be working in ChatGPT as an assistant. And what's interesting is that post-training step, because of the way it works, gives a lot of color into the types of things that artificial intelligence will be really good at. So my basic metric for whether or not a task can be automated by an AI is, can the task be cheaply verified, and can the task be cheaply benchmarked? So for example, on a coding task, both of the answers to this question are yes. If you want to check whether a piece of code works, you can compile it, you can run it, you can check whether the output was correct, and if you want to measure performance, you can just measure how long the code took to run. And all of those operations are extremely cheap. And so what that means is that the coding models have been extraordinarily good. They have, we basically, last year in October, most of my founder friends and I were using AI to write about 30% or 40% of our code. In December, the models actually crossed the threshold where, because they've been so well trained on all of this live data from basically running code and figuring out whether it was cheap and whether it was correct and whether it was fast, and getting all of this live input from live deployments. It's now nearly 100% of the code that most people, at least in the technology sector in the Valley, right, is being written by an AI to first order. And that's not an exaggeration. Like, if my engineers' workflows have actually fundamentally changed, and they don't really write code by hand anymore, except in really niche circumstances. They're mostly nearly 100% of their job is talking to assistants. In contrast, something like creative writing is actually pretty hard. And that's because if we go back to that test, how do you cheaply verify and cheaply benchmark that a piece of creative writing is good or bad, right? You can check whether it's grammatically correct and syntactically correct, and you can check whether there are spelling errors, and you can check whether it's written at a 12th grade level or at a 4th grade level, maybe based on things like vocabulary and sentence structure. But beyond that, it's hard to come up with an easy way to compute. Okay, like, how do I tell whether this is how do I tell whether my writing or Asimov's writing is better? And so the things that immediately come next after coding, lots of knowledge work. So things like manipulating Excel spreadsheets, filling out tax forms, basic diagnostics, basic paralegal work. I anticipate most of these things will be gone by the end of the year. Things that require a human in the loop, things like nursing are probably safe. Things that are also physically constrained are also difficult to post-train. So this is why robotics is hard, because the live data is, in order to do that, sort of like next training step, you've got to go deploy robots, and you're physically constrained. Although there's been a lot of work in trying to basically put robots into simulators and speed that up. So that might not be true for too much longer.
So I want to jump back, because I caught a phrase you said in there, and I think it's worth having you expound a little bit on it. You said by the end of this year, the replacement, a lot of this. And of course, there's a lot of debate and consternation over what jobs are lost or what aren't going to be lost and things like that. You're talking about a speed of application implementation deployment that is significantly faster than we've seen in other technology cycles.
So part of this is that I think everyone just underestimates what the models are already capable of doing. So to level set, as of today, the models that you and I use in ChatGPT are capable of doing pretty astounding things. They are, as an example, like, it can control a web browser fully. So it can navigate to any website, click on any link, fill out any form. Claude actually the Anthropic guys actually just released a new tool yesterday that actually not only allows it to control a web browser, but actually allows it to control an entire computer. And so part of why I say, hey, there's this category of stuff that's going to be automated by the end of the year, um, is just that the capabilities have just arrived so fast, and like the capability state where we are right now is that it's not theoretical; it's happening. I think that thing that I mentioned earlier about that transition in coding models was quite frankly shocking to my peers in the technology sector. We were using AI 12 months ago, and 12 months ago it was like, all of us were like, yeah, like the code's getting written and it's pretty good, but it's not incredible, and I still have to write code by hand, and it took 12 months, and no more than 12 months for that to just for basically an entire industry to effectively become, and an entire training set to effectively become obsolete. There's lots of debate about, okay, like what does that mean for the underlying jobs? But in terms of the work is dead. We don't do that work anymore.
So, so one thing that to keep in mind about this is that there's an accelerating takeoff here, where once people start using one of these AI tools routinely for a given task, the AI tools rapidly bootstrap up to getting better and better at it because they get more and more data on what is good versus what is bad. And so you go from these tools being, just good enough to be able to barely use for a given thing to being strictly superhuman very, very, very quickly. And it's really counter to our intuition from previous technological revolutions. So if you look, for instance, at the internet boom, back in the 90s, early 2000s, that's the reference point for a lot of people, and it's the wrong reference point because back then what you had was a lot of excitement about these new technological capabilities, but the revenue wasn't there, right? There wasn't actually a lot of business being done on the internet because you needed all of this infrastructure, right? I used to make fun of people who were graduating from Caltech in my class about going off to sell cat food on the internet, right? I thought it was the most ridiculous idea ever. Guess where we buy all our cat food now, right? The issue is there was all of this just-in-time delivery stuff and all of this physical infrastructure and all, we didn't have cell phones in our pockets that could get to the internet. Like that didn't happen until 2007, I think, when the iPhones came out. So like the physical hardware infrastructure, the business infrastructure, the ability to do credit card transactions online, broadband to the home, like all that physical infrastructure wasn't there. And so there was a lot of excitement, but not a lot of revenue. What we're seeing now is something completely different, which is we're seeing companies that are growing at a rate that is, in effect, unprecedented in human history, right? I had some founders who I interact with who were complaining to me, this was a few months ago, that their company was only growing by 40 something percent. And I said, 40% per year is very respectable. This is me being old. And they're like, we're not talking about per year. I said, 40% per quarter is astonishing. They said, no, 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 it's not 40% per quarter. It's 40% per month. I said, what do you mean you're disappointed? Are you trolling me? Are you joking? And they're like, no, the guys over at, and they named another place in the space. They're like, they're doing 70% per month. And that was one of those moments where I realized, not in Kansas anymore, because the rate at which some of these companies are growing on existing infrastructure is astonishing. The comparison I make is to the 1870s. It's the founders' years in Germany, when they went from doing a handful of companies a year to doing thousands of companies a year, and when they built out their railroads. Because the thing about railroads is that there's this network effect where every time you bolt on another spur line, the value of the overall network goes up. We're in a similar situation here, but it's going much faster.
So let's pick up that line. When we look at this, AI has been identified as one of the major strategic elements in global competition, U.S.-China competition and in the future of nations, whether it's economically, whether it's militarily, whether it's through information warfare or information dominance, AI's at the center. And we talk about underneath that, we have this very large supply chain of the technologies that go into it. And so the competition in AI has been moved down to the physical product. It's been moved down to the semiconductor competition changing the structure of the industry? Where are things going to be built and how do we move them? And then it's in the secondary piece, which is, of course, electricity, right? Powering the system. Why, if AI sits at this center, it's moving so fast, it is so critical, why are we not seeing more rapidly a shift in the geographic location of the manufacturing backbone of the semiconductor industry? Why are we not seeing it fragmenting and being built in competing environments in different parts of the world in that competition? And instead, we continue to see certain places be very, very sticky, even if they cross over geopolitical competitive boundary lines.
So your question is why are these things not more portable at the hardware level?
Pretty much, yeah, because the physical technology is known. Why is everybody still in Taiwan?
Yeah, so this is mostly a function of things other than the core technology, right? From a core technology standpoint, if you want to talk about fabs, Intel, Samsung, TSMC, they all have the technology to build really advanced transistors at scale. Um, Used to be that there were 10 or 15 places that knew how to do it. If you threw enough money and some time at a place like Global Foundries, they could also do it, right? They could do 3 nanometer transistors. The issue is that it's everything else that gives this ecosystem momentum in Taiwan. So the first piece of it is that it's not just TSMC. It is all of the upstream and downstream capabilities around TSMC. So you have all of their suppliers, you have all of their first order customers, you have their packaging vendors, you have their test vendors, you have design partners, and everyone knows each other. It's a small state. I mean, it's easy to joke about it that everyone is each other's cousin, but there's some truth to it, right? You go to Taiwan, you engage with that ecosystem, and it's very possible that if there's a problem with something you're doing, that problem may get solved without you ever even seeing it, because your 3 vendors who are, the chip fab and the test vendor and the packaging vendor, they may get together without even talking to you and just figure out how to sort out your problem because they're all geographically concentrated and they all know each other. Whereas if you tried to do it here, you'd end up in a blizzard of finger pointing, right? Because you don't have those kinds of strong personal relationships and geographic concentration. The second thing is that TSMC has a very powerful network effect mode, which is if there are all of these places that generate semiconductor IP, which is the design of essentially sub-chip components, and these components could be billions of transistors on their own. So you go to Synopsys or you go to Cadence or you go to any of a variety of other places, and you can license the designs of sub parts of your chip. And what that means is that most of the places taping out modern semiconductor chips at TSMC, they're only designing 1% of that chip, 5% of that chip. There's nowhere else you can go where you get that ecosystem because those IP vendors, it's not worth their time to go do that IP in Samsung and Intel because there isn't enough of a customer base, right? So there's a self-reinforcing network effect monopoly at TSMC. The third thing is that in Taiwan, every middle school kid knows what a wafer is. They know what a stepper is. They know what an etching system is. The government officials, if you go into a government official in Taiwan, you say, oh, well, it turns out that there's going to be this boom in silicon photonics, and I want to set up a test and packaging floor to service all of these hyperscalers who are going to want to do test on silicon photonic chips. Their question is, oh, are you doing it at 200 millimeter or 300 millimeter? Right? They're utterly conversant, utterly knowledgeable. You don't get that here, right? You don't get that in Europe. It's because Taiwan has specialized in this as their national endeavor. And the level of cultural understanding and focus on this ecosystem in Taiwan is just astonishing. So Yeah, you could set up a fab here in the US. I mean, Elon is getting ready to do it, and he may be very successful, but it's a much harder pull to do this somewhere where you don't have the rest of the ecosystem and bootstrap up that whole ecosystem all at once. The other thing is that TSMC is good at something that neither Samsung nor Intel is good at, which is they run a high mix facility where there are thousands of customers running thousands of different designs, and every customer only cares about their own design. Samsung and Intel are set up to do a few products and do them very efficiently and do a lot of one thing or a lot of a handful of things. Running a high mix facility is extremely difficult, and it's about how you interact with your customers, what data you expose to them, what you tell them, how you keep a huge flock of customers happy. So being a fab and being a foundry are two completely different activities. TSMC is the world's greatest foundry. These other guys struggle to be foundries.
So what we have a short amount of time left, unfortunately, because we've got a lot more issues to go over here, but we'll keep addressing this over the next couple of months. What would you say if you were talking to, not to a technologist, not to a venture capitalist, not to anyone else, but to these geopolitical analysts, the security risk analysts, the supply chain analysts within companies that are not necessarily directly part of the semiconductor supply chain, or building out the data centers? What would be the 2 or 3 things that you think are very important for them to keep in mind as they're trying to look at and integrate this extremely rapid technological change, but simultaneously this real difficult movement of goods or movement of manufacturing as they're thinking about the future?
The one thing I would say is that I would remind every analyst, every individual, that's thinking about this problem right now, is that humans are phenomenally bad at intuitively understanding exponentials. And the thing that they should keep in mind is those first 3 months in 2020, when everyone said, "Hey, like this COVID thing, it seems like kind of bad," and then over a 2-week, in the beginning of January and by the end of March, it was a global pandemic and a global shutdown. That's an example of all of us understanding that this virus was an exponential, and us still failing to intuitively comprehend what was happening. The application and the advancement of these intelligence algorithms are an exponential. I think despite the fact that everyone logically understands this, I suspect that everyone still underestimates how rapidly these technologies that are better than individuals at nearly every form of knowledge work are going to arrive very shortly. And so calibrate timelines accordingly is the single thing that I would say. It's actually really good that there's the COVID reference point, because everyone knows what it's like to fail to understand an exponential.
Yeah. One thing I would pay attention to is the human factors, which is there's a lot of situations where the technology is going to run very far ahead of the human institutions. So that's going to create disruption, but it's also going to create pushback. If you look, for instance, at the legal profession or at the screenwriter's profession, these are places that have very strong, in effect, union protections. And those unions, and we saw this with the screenwriters, they asserted essentially a monopoly on the use of AI tools in order to protect their people. And so you're going to end up in situations where groups of people attempt in some way or the other to assert a monopoly, either through commercial means or unionization means or sovereign action, in order to protect their jobs. You look at the legal profession, right? I guarantee you that the Bar Association is going to say a human has to be in the loop for certain things for legal purposes, regardless of whether the AI is objectively better or not in some cases. And so I think that one of the things you're going to run into is that there's going to be a lot of resistance to this. And the interesting feature of this is going to be that you're going to have some sovereign states that attempt to regulate this in such a way that they create incredible disadvantage for themselves compared to places where those regulations aren't as powerful. But on the other hand, there's going to be an interesting balancing act between promoting social stability and promoting the use of cutting edge capabilities.
So I guess for me, there's a couple things that come out here on this last point. It is think about port automation and the countries that have embraced port automation and the countries that haven't, and the differential competitiveness of those two. One preferenced the union and the individual, the other preferenced efficiency, and we see big differences in capability, capacity, things of that sort. And I'm guessing that for a physical reference point, in some ways, that's what you're getting at.
Have the places that privileged automation just dominated the space? Like how has that played out?
Oh, sure, the port of Rotterdam is much better than the port of Long Beach, um, and and we can think about its processing capacity, the number of ships that can go through, the number of containers it can move, how quickly it can do so, everything like that. It just really has shown competitive differentials. And I think, part of what
I
you're
guess
talking about is
I
that.
guess I guess what I'm wondering about is like the port of Rotterdam and the port of Long Beach are not replacements for each other because they access different markets. Are there examples where you have two ports where they're in different sovereign states? One embraced automation, one didn't, but they're close enough to one another that there was a competitive situation between the two.
We can go and dig into those, but I think that the raw capability and capacity that we see in certain countries that embrace this technology allow them to accelerate their own capabilities faster than what we're seeing in other countries.
Fascinating. Yeah, no, I think you're right. I mean, this is going to be a similar situation. I think the difference with a lot of this knowledge work AI stuff is that it is extremely portable, right? Corporate America proved that it was relatively easy and many fortunes were made moving a lot of stuff to India over the course of 20, 25 years. That is all fundamentally knowledge work of one sort or the other, like all of the IT call centers, that kind of thing. The speed with which you can remove all that stuff is it's just going to be incredibly fast.
The other thing to mention, Roger, and this goes a little bit understated, but one of the things I think any analyst should be thinking about is who's actually got compute to run these models. So, like one of the big problems that all the labs have right now, like OpenAI and Anthropic and DeepMind, and there's too much demand and there's not enough chips, and they're like all the chips have been bought, and all the chips have been bought for the next 24, 36 months. So there's one question of like who's got the chips, and you can think about this in terms of uh, which nation states have chips and which geographies have chips, which geographies have the ability to make their own chips. Whereas I think for thinking about things like the development of new models, you can really still only make things at TSMC. For thinking about things that are the deployment of new models, so things like inference, where you're just taking a model that has already been trained, where someone's already spent $1 billion to do the development and is just trying to figure out how to make it go fast. There are a lot of other places that you can go where you can use more trailing edge technology, but take out a lot of the general purpose things and just hard code, one or two things about your model into the chip, and those things work. And so thinking about not only the who's got the compute and who's got the data centers, but also who's got the capabilities to build which parts of the training and inference stack. I think those things go super understated.
What one of the interesting dynamics we've seen is that tokens are sort of the currency of the realm in this space. Certain kinds of like you would expect at equilibrium that as you get new generations of chips and new generations of AI compute, that older token costs that are associated with older chips would always be getting cheaper. And over the last 4, 5, 6 months, certain kinds of tokens have actually been getting more expensive because demand is outstripping supply, even as people are bringing online billions and billions of dollars of of new compute. The issue is that the ecosystem for making these chips and putting them in packages and putting them on boards and deploying them to data centers, that ecosystem is set up to, if over the last 30, 40 years, if you really wanted to press the gas, maybe you could double capacity end to end in a couple of years, right? In an upcycle. The demand is expanding much faster than that. And so one of the interesting dynamics that we're seeing is that capacity is shifting from less valuable chips in things like consumer electronics, like DRAM, into more valuable chips that are used for AI, like high bandwidth memory. And so there are a lot of consumer electronics things that are either going to get a lot more expensive or go out of business because the chips that they need are not high enough value to occupy space in the fab anymore.
The one other thing that I'll mention is to use your port analogy, Rodger, one of the things to pay attention to is which countries and which nation states decide to prioritize compute as a strategic resource. And I think there are places that have, and there are places that haven't. In an increasingly stratified world, and an increasingly polarized world, and places where technology isn't flowing through all the channels to all the places. I think the people who hoard compute are probably going to be at a material advantage. I mean, look, they're bombing data centers already.
With that, we are going to have to cut this now. There's a ton more we need to go in. I really want to thank you both for joining me. Marcus, you've made me feel that at least AI doesn't know which is better, Hemingway or James Joyce, in writing yet. So at least there is some hope for humanity out there. But I think that the issues that we see here is it really does play into the complicated geopolitics of this. You have it in the physical supply chain, you have it in the compute chain, you have it in the energy, you have it in government regulatory dynamics that incentivize or disincentivize. You have it in the corporate dynamics that may not be matching the way in which the governments are looking at this. And so there's a whole variety of elements that we have to look at in collaboration if we're going to truly assess how such a rapid pace of technology development is going to impact the structure of the geopolitical system. So thank you both for joining today.
Yeah, of course.
And if you'd like to keep up with what S4GEO is doing, you can, the Society for Geopolitics, you can find that at s4geo.org, and follow us as we continue in our series of podcasts, webinars, and stay tuned for information about upcoming in-person events. Thank you all.
The S4GEO Podcast is produced by S4GEO, the Society for Geopolitics, a 501c3 nonprofit organization. The views and opinions expressed by our guests are their own and do not necessarily reflect the views of S4GEO or its leadership. This episode was hosted by Rodger Baker, founder of S4GEO, executive producer Maggie Laszlo, producer Christine Clay, produced and edited by Matt Russell. Thank you for listening. To learn more about S4GEO, visit us at www.s4geo.org and follow us on LinkedIn.